Included in ASAP 2013 is an enhanced calculation for determining the amount of energy that scatters towards a region of interest that is below the horizon or partially below the horizon of the scattering surface of interest. Here's what we're talking about. Here's a simple example where I have light coming in and striking a surface that has a scatter profile associated with it. In reality, light that hits that surface would scatter into a full hemisphere, but different amounts of energy would obviously go into different angular regions of that zone, depending upon what exactly the profile of the scatter was. In this particular case, what we've done is defined a region of interest using what we call an importance edge, and we're only interested in the amount of energy that can scatter from this surface towards this region of interest. And what ASAP will do is, as you'll notice, all of my scattered rays that were generated go to my region of interest, but also ASAP has appropriately scaled the total energy that reaches that zone based upon the angular subtents of that importance edge relative to the sample, the properties of the scatter, BSDF, etc. So we're doing a complete calculation. You don't have to trace a huge number of rays to capture that small number that would in reality go to that region. It gives you a much more efficient way of doing stray light and scattered light analysis calculations, which is a very important usage of ASAP by a large number of our ASAP users. But there is a problem that can occur if the region you're interested in is partially or almost completely below the horizon as seen by your scatter surface. So in this particular case, again, let's zoom in a little bit. So here's my surface of interest, and in this particular case, my importance edge being above it will capture a significant percentage of the light or would be seen by that surface. But what if I had a slightly different situation, and let me look at that here, where instead of scattering in this direction, we were scattering in this direction. Again, since this surface can only scatter into a hemisphere, when I position my importance edge over here, only part of that edge will be filled because it's impossible for the scattered light to go below the horizon. So what we've done is enhance the calculations that we use to determine how much energy would actually be seen in this region of interest. So let's take a look at the results from this calculation. And in this particular case, you'll notice that my elevation angle, I've got set from -10 to 10 in this particular graph. The 0 point is where the center of, in this case, my importance edge, a rectangle, is relative to the axis. So since part of the edge is above and part of the edge is below, I still have some energy that will scatter towards that edge. But as my edge elevation angle is such that it is entirely below the horizon, then of course I would expect to have no energy traveling through that edge, and that's exactly what we see. And this calculation applies whether we're talking about defining an importance edge or possibly scattering the light towards a point where, again, we would have the situation where part of the cone would scatter below the horizon, which of course is non-physical. So we would reach a point where 0 energy travels towards that point. But as we go through the center, we start to see the fall off as parts of the cone get clipped off until we reach the point where all of the energy would fail to make it through that particular region of interest.